we're going to finish up our discussion of the electric potential primarily by doing some examples. And so let's look at some examples where using the electric potential can be a very beneficial approach. So here's an example called approaching a charged sphere. So a proton is fired from far away at a 1 millimeter diameter glass sphere that has been charged to 100 nanocoulombs. So it's got a total charge of 100 nanocoulombs. What initial speed must the proton have to just reach the surface of the glass? And so I drew a picture here. So basically, we can think about this problem as having the before situation. So it's launched off with some velocity towards this sphere. And then after, what we want is the proton to sort of just come to the tip of that sphere and have its velocity be 0. So we think about this problem, and hopefully you've sort of thought about this, but in a case like this, all right, so as you might think, well, hey, let's try to use kinematics. Here's the velocity. I'm heading towards this over here. Let's find the acceleration. All right, so what would the acceleration be? Well, we'd say F equals ma, right? And what is our F? Well, our F is something like this, K1, K2 over R squared equals ma. Now, here's the problem. Okay, so suppose I take this and solve for a. So I bring an m over here and find the acceleration. So this depends on the r between them. And the problem here is that the r is constantly changing, right? So the force starts out pretty weak, and as this thing gets closer and closer, the force gets bigger and bigger. And so this is not a constant acceleration, so we can't use kinematic equations. Now, we could integrate the acceleration and do things like this, but I think our general rule is let's only integrate if we absolutely have to. And so this is going to be a problem like this, where the electric potential, and thinking about this in terms of electric potential energy, can be very beneficial. Another hint, I think a lot of questions we get are sort of, how do I know what to do on different problems? And so when you're thinking about using mechanical energy, all right, so what are some of our equations for using energy? Well, there's our kinetic energy, which is 1/2 mv squared. There's our new one, our electric potential energy, right, which looks like something like Q times delta V, right? So our electric potential energy is Q times V for some kind of an object. The V, the electric potential, will often depend on distance, right? So the electric potential from a point charge is like KQ over R. And so if you look through these equations we got, the sort of things that we have in these equations are like the velocity and the position, right? This R will oftentimes give us some sort of a position in our problem. And so a key thing for us is if our problem only sort of gives you or is asking about speeds and distances, then energy is, in general, I would say, sort of a great way to sort of start off thinking about that. So that's sort of a tip. So like in this problem here, we're given the initial velocity and we're given the final velocity. It's sort of buried in the question, but it's there. And then we're told, given some information again about distances, the fact that it's super far away. And so that's just sort of a tip that this could be an effective approach. And when we talk about energy conservation, so conservation of mechanical energy, so again, this is, something that we did in mechanics. There's the before and the after. So the key is sort of coming up with your two different times. And so in this case, it's the before and the after. And so if I do this here, let's just go through and write a couple of characteristics. So the charge for electrons and protons is this thing here. So that's kind of nice to write down. Again, we're dealing with a point charge. So we're going to deal with this glass sphere, right? It's pretty small, so we're going to consider it as a point charge. And that's the charge for that guy is like 100 nanocoulombs. And so let's think about this. So we got an equation sort of like this here. And so this would be our after and our before. Now, everyone does this a little bit differently, so maybe yours is a little bit different than mine, but we sort of will end up doing the same general approach. And so we've got the kinetic energy plus our electric potential before and after, and I want to set these up equal to each other. So that's the trick. And so let's look at this, okay, and think about the before. So the before, so these formulas here, you would have 1/2 mv squared, where this would be like the initial velocity, and then I'd say plus, so now this over here, if you remember this equation, the q is the q that's moving, and so I'm going to call that E. So that's just, our fancy way of writing the charge of either an electron or a proton is E. So that's just in there for the q. And then the potential is the potential from a point charge. So it'd be kq, sorry, beg your pardon. So E, K, and then I called the charge of that one guy, the big capital Q, over the initial distance. And so that's our before situation. So let's look at that and go back and sort of look at that picture. And so a proton is fired from far away. So this is the kind of thing books love to do. So what does that mean, far away? Well, that means that that distance r is infinite. Okay, it's like super big, right? And so over here, what we can sort of say is, well, if r is super big, then essentially this term just goes to 0. So I can just sort of forget about that term. Now over here on this side, we'd have 1/2 mv final squared, and then plus again, so the charges are E, and our potential equation is K big Q, and this would be now over R final. Now in this case, right, if you go back to our picture, so what we want is we want to find, again, the initial speed must the proton have to just reach the surface of the glass. So that means at that point, our V final is 0. Okay, which in turn means that this term here is 0, and then that R final, right, is just the diameter of the glass sphere, so 1.0 millimeters, something like that. And so this turns in, again, what will oftentimes happen with mechanical energy conservation is our math isn't too bad. It's again something that's the tricky part is setting it up, right? So it's usually, and we didn't have to integrate, which is really nice too. And so when I solve for this myself, I got that the VI is equal to an equation like this here. So 2EK, or big Q, divided by, now this M would be the mass of a proton. And again, this is something you can look up. But it's 1.67 times 10 to the negative 27 kilograms. And when I plugged everything into here, let's see, I forgot the R final. When I plugged everything in, I got 1.86 times 10 to the 7 meters per second. So maybe just check on that one and run through it. But again, this is the kind of thing where electric potential energy can be super helpful to us. And so in this case here, you can see that it was really advantageous to do it this way. So let's look at another example that's a similar kind of situation. And so here we have a situation. We've looked at this before in different circumstances, but let's look at it now and we're going to go through and solve it all the way. So an electron follows the trajectory shown from I to F. At point F, how would you relate the velocity at point F to at point I? So stop and think about this one and we'll talk about it in a second. So basically, which velocity is bigger at I, at F, or are they the same, or is there not enough information? So think about this. All right, so I got C, so hopefully you agree with that. Now let's think about this. There's a couple different ways to think about this. So first of all, as this charge, so we've talked about this one before, and so the force, the electric force here, if you sort of follow the trajectory of this electron, the electric force is hindering the motion. So the work done by our conservative force is going to be negative. All right, and so basically we know that there's the law, the kinetic energy work theorem. So the work is equal to the change in the kinetic energy, right? And so basically, if there's negative work, we're hindering the motion, and so that it will tend to slow it down. And there's nothing else here that's doing work, right? So these two forces or these two objects are interacting with each other, and nothing else. So it's the only thing doing work. That's one way to think about it. We talked about this one previously in terms of what's happening to its potential energy, its electric potential energy. And we got the idea that in this case, the electric potential energy is increasing, right? Because basically as it goes from here to here, you're increasing the amount of energy. This is essentially equivalent to, like taking a book and lifting it up 3 feet or something, right? You're increasing the the potential energy of the book, and here by taking the electron, which wants to get close to this positive particle, and moving it away, right, you're increasing its potential energy. And so if you increase the potential, then that means the kinetic has to decrease. And again, what's happening in this problem is, we don't know what happened to this particle in the past. And so obviously at this point I, it has some velocity that's sort of in this general direction, right? And so basically it sort of keeps up with that velocity, but because of the influence of the positive particle, it starts to sort of turn, right? And so it's sort of a weird problem in that we sort of got this snapshot. We don't know what happened to it in the past, but we can still tell an awful lot just from the picture. Now, if you wanted to actually, say, find the speed of the electron at this point, this would then again sort of be a similar sort of situation to what we did previously. So let's just go through here and we'll list a few things. So I'll call this Ri, so the initial distance between the charges, and that's really bad. Try it again down here for the R final. This would be my R final. And again, over here we got some sort of V initial and a V final, and this is our electron. So it's a negative E, the same charge as we had previously, or the same size of charge. And again, what's happening here is this is going to be the interaction of point charges. So VKQ over R. And I think what I decided was just to call this big one, this capital Q. And again, our potential energy is Q times V. And so just the same situation as before. I like to say final equals to initial, but of course you can do it any way you want. And so here I'll set up my equation like so. So that's our good old friend, the kinetic energy. And then here, so now the charge that's moving is a negative electron. So I'll put negative E, and then our equation, KQ over the distances. And so this would be my R final. And over here I'd have 1/2 mvi squared minus E K constant Q over R initial. And this is essentially our general formula for this, right? For when 2 point charges are interacting and we want to find how the kinetic energy or potential energy of them is changing, something like that. So what I would do here, so this is one of these kind of exercises where we don't have numbers. So I would multiply the whole thing by a 2 to get rid of the 1/2, and then divide everything by a mass. And so that gives us sort of a little leaner equation. So VF squared, and then this guy here would be negative 2K E times Q over R final equals the initial squared, and this would be negative 2K EQ over R initial. And then what you can do is then just isolate the VF and get something along these lines here. So if I bring this one over, I'll get a 2K EQ over M. I forgot the 2 factors of M here, pardon me. Again, so we were dividing by M and multiplying by 2 throughout the whole system. And then it would look like this here. And then, of course, the square root of this. And so this would be our final answer. And then also, I mean, this is probably a little bit more work than you'd want to do in this situation before that previous problem, right? You could look at this now and say, okay, Ri is less than Rf, right? So I know that my initial distance is less than Rf. So you look at this piece right here, 1 over Ri. So since 1 over Ri will be bigger than 1 over Rf, this term will be positive, which means this overall term here will be negative. And so that implies from here that you're going to take whatever your Vi squared was, subtract something, and then get V final. So it implies that V final is less than Vi, which is of course what we got in that last clicker question. And again, this is overkill, but it's just nice to kind of make sure that when you're done that your equation actually agrees with your expectations conceptually. So now we move on to our last relationship between the potential and the electric field. And so if we start, we had this equation that said the electric field in some direction, like the x or y direction, so here we call it the s direction, just to keep it general, is equal to negative dv ds. And so what we can do is take that equation and basically sort of take it apart a little bit. So I can say dv equals negative es ds. Just literally taking this and sort of doing a little bit of algebra to it. And then what we can do is take the integral of both sides. So the integral of dv equals negative es ds. And when we do this, we could always, when you're doing over here, say that I'll do this at points vf and vi. And so this integral just gives us over here this delta v, which is of course v final minus v initial. Then it equals this integral here. And so to go from the potential to the electric field, we take a derivative. So hopefully it makes sense. Fundamental theorem of calculus type stuff, that to go from electric field to potential, we need to integrate. And then you can see that hopefully that if you're looking here at es ds, the sort of generalization of this would be e dot ds. And so we can always find the potential difference between 2 points if we know what the electric field is. And also just a graphical interpretation of this is that the v final equals v initial minus the area under the es versus s curve between the 2 points in question. So we can look at a question sort of like this here. So there's a figure here with a particular electric field in the x direction of 100 volts per meter over a period from 0 to 2. And so we want to know is which one of these figures is the best graph of the potential versus x. And just sort of assume that the potential is 0 at x equals to 0. We're going to find, and maybe you've already found it, that the potential is like height was in mechanics, and in general we can just sort of call it 0 pretty arbitrarily. We're only really going to care about differences in potential. So let's call it 0 at the position x equals to 0. So give this one a go, and we'll talk about it in a second. Okay, so hopefully you got choice E. So let's try to unpack this a little bit. A couple of different ways to think about it. In terms of this graphical interpretation. So here's the potential versus x. And so here, so we'll start here. This will be our v initial. And we'll sort of look at this as like 0.5 and 1, 1.5 and then 2. So just kind of to sort of do this as accurately as we can. This one over here. And then over here we'll have 50 and 100. And so again, VF is equal to VI, which is 0, minus the area under the curve here. So let's, for instance, look at this piece right here. So in going from 0 to, again, this would be the point 0.5, the area is 100 times 0.5, so it's 50. So 50 volts. And of course this is volts here. And so when I come down to this point, I get to that point there at 50. If I do the next one over here, again, just to show you that this area under the curve, right, which is sort of a weird thing, but it's 100 volts per meter, and then this is times 1 meter. The meters cancel, and I get 100 volts. So after a distance of 1, I get 100, and you'll find that if you do 1.5, you get 150, and then 2, 200. So it's a nice decreasing slope line like that there, just like the picture we had. And so that's the more the graphical interpretation. Of course, if you were to look at this, delta V, sort of more calculus-like, maybe, so V final minus V initial equals negative ES ds. And then I'll do this from the position 0, which is our initial position, to just, whatever value. And so, yeah, let me just switch these to be x's, since this is the x direction. And we'll do this to whatever value of x we decide to go on. And so if I do that, I can write this as v final equals vi minus this integral. Now, the key kind of point here is that, if I'm doing this calculus-wise, I can just pull that electric field out. So it's Ex. I can just sort of pull it out there, 0 to x dx. which just gives me delta x, or just sort of x. So this would be vi minus the ex times x. And so you see that this is just the equation of a line, with the slope of e to x there. And so since we called that 0, it would be this sort of line here. So as usual, couple different ways to sort of think about it, but hopefully that makes sense. So this is again how to do we talked last time about how to go from the potential to the electric field, and we did some examples, and now we're doing the opposite, going from the electric field to the potential. So we should be able to have the flexibility there. Now here's another example. Now technically we don't need this because we have enough sort of equations and stuff to sort of handle problems like this, but this is just a little bit of a more convenient way to think about it. And if you find solutions in different places, they'll sort of use this formula, but it's really just the same formula we had. But what we can do now is say, well, let's look at a picture here. So we got a Q1 and a Q2. And imagine that we're watching the Q2 is being repelled, and so it's going like this way, and it's feeling some electric force from the Q1, so it moves some distance from x initial to x final, and we want to ask ourselves, okay, what's the work done? Well, we already know how to calculate this, but we can also do it here with an integral. And so the work of the electric force would just be the integral of force over distance, right? That's again something from mechanics. Now our force equation is Coulomb's law. And this just looks like our regular Coulomb's law, except that here we're actually writing this distance as x. Because in our particular problem here, the distance of separation between these two particles, we're measuring it in one dimension in the x direction. But you could have called that direction r if you really wanted to. And so this works out to be not that bad of an integral, right? X to the x, 1 over x squared. The antiderivative is negative 1 over x. And then evaluated at the endpoints. And so we're looking at the work done from going from x initial to x final. And so when I plug in for that, I get this situation here. And then what we say is, well, we know that the work done by a conservative force, which is the electric field, is the negative of the change in potential energy. And so from that, we can sort of see that over here, this would be equal. This over here would be our equation for the potential energy. And so we can write the potential energy between 2 point charges as K, Q1, Q2 over the distance of separation. Now so far we've been writing it as Q, the Q that's moving, times the potential. And so since they're both point charges, we've essentially gotten that same formula. But it's just nice to sort of think about it sort of from a new way. So we can get it from here, and it's anytime there's two charges, the electric potential energy between them can be written as Q times Q over X. And it can sometimes just, thinking about that can be a little bit handier, I think. So it's nice to kind of summarize that. And then, so that sort of thing, then we can solve, again, sort of problems that we can't solve as easily with forces. And so here we have an interaction between two elementary particles, causes an electron and a positron. A positron is just a particle that's a positive electron, to be shot out back to back with equal speeds. What minimum speed must each have when they are 100 femtometers apart in order to escape each other? And so again, this is the kind of thing where if you look at the problem, we're dealing with distances and speeds, and so that's a key. Right? When I'm only dealing with distances and speeds, that energy might be an advantageous way to think about this. So why don't you think about this one, try setting it up maybe, and then we'll talk about it. All right, so hopefully you had a chance to think about this one. And so here's a picture. And so again, so the interaction between two elementary particles causes the electron and positron to be shot out. What minimum speed must each have when they're 100 femtometers apart in order to escape each other? And so the way I set this up, as I said, before is this. So before is there's the two particles next to each other, and there's a distance between them, Ri, of 100 femtometers. And afterwards, right, it's the kind of case where, again, it's not necessarily super clear, but what they're saying is you want these things to be infinitely far apart and have zero velocity. Okay, so it's sort of a kind of a weird situation. And so let's go through and try to look at this. So again, our key here is conservation of mechanical energy. So the only force acting between these is the electric force, and that's a conservative force, so we're going to conserve energy. And so let's just write out a few terms. So 100 femtometers, I had to look this up, but that's 100 times 10 to the 15 meters. So that's like an atomic scale. That's why it's so tiny. The mass of the electron has the same mass as the positron. And you can look that one up again too. So it's 9.11 times 10 to the negative 31 kilograms. And of course the charge for both of those is 1.6 times 10 to the negative 19 coulombs. And so again, just, the positron is the anti-particle to the electron. And so it's basically identical, just has a positive charge instead of a negative charge. And so if you look here, this situation comes up, which this will happen sometimes, which is really weird, where basically the K final, or the energy final, the way we've defined it, is all zero, right? So what is our equation here? Be 1/2 m v final squared plus our new equation here, K Q1 Q2 over R final. So if you look back at our picture, right, our R final is infinity, and we're assuming that the velocity of these two guys is 0. And so, and another little trick I'm going to do here is I'm going to erase this 1/2, and sort of the idea is that we have 1/2 the mass of the electron plus 1/2 the mass of the positron. Those are identical masses, and so that equals basically just the mass of one of them. So we'll call it maybe mass of electron, whatever you want to do. And so over here, I can sort of write it in that fancy way, just dropping the 1/2. But either way, the velocity final and the R final are both a 0. So the final side of this equation is completely just 0. Okay, which means we're going to have some interesting ones on this side, and we do. So for the kinetic energy initial, again, I'll say mass of electron. I'll drop the 1/2 because basically they're both moving. And in this case, they both are shutting off with identical velocity. So we can have them have the same velocity, vi squared. And then at the final case, our equation here will be K E squared over R initial. And so the negative sign came because in that equation, we're going to have K times one of them is just E, one of them is negative E divided by their Ri. And so when that works all out, it'll be negative K E squared over Ri. And so basically, we then just take this equation and go through and solve for it. And so I bring this over, so I'll have M E vi squared equals K E squared over I initial. And so I got a velocity initial to be K E squared over mass of electron Ri, and of course that's square rooted. So when I plugged in my pieces, I get a speed of 5 times 10 to the 7 meters per second. Okay, so another example here. So again, when you're only asking for things, there's a couple ways to think about this. When you're only, as sort of a hint, problem-solving hint, when you're only asking for things like speeds and distances, energy is a thing to think about, and more fundamentally here, the interaction between these two particles, that's a conservative force. The only thing that's working between these particles is the electric force that conserves mechanical energy. So it's a nice way to start out thinking about a problem like this. So we just developed this new equation for the potential energy between 2 point charges, and technically it's not really that much easier maybe to use it than what we were doing before. But the place where it becomes much easier is if you have more than 2 charges. So let's say, for instance, you had, sort of 3 charges set up, and I'll call them, Q1, Q2, and Q3. All right, and so here's where, and you want to define, say, the potential energy that's held in all 3 charges. That's where this thing really pays off. And so if you want to define the electric potential energy of all 3 charges, you basically use this equation and sum up all the contributions. Now the tricky part is this sort of summation restriction here, which basically says you just don't want to double count. And so what that means is if you had, again, this place here using 3 charges, and by the way, if there's more than 3 charges, the person writing that problem is not very nice. And so you'd say, let's do this first one first. And so this guy, I'd say, well, I'd do K, Q1, Q2 over the distance between those guys, which I'll call R1, 2, which, you know, is just the separation distance between those. So then you do the next one, which would be these two guys here. So I'd say plus K Q2 Q3 over R23. And then finally there's one more here to do, and that would be Q1 and Q3. And the distance between those would be R13. And so again, you know, you don't want to double count. So there's basically, you want to have a contribution for every pair of charges. And so here that would be Q1, Q2, Q2, Q3, and Q1 and Q3. And that's just, again, this is a much easier way to express the total electric potential energy of more than 2 point charges. And so you can imagine if 4 charges, it's the same idea, but just more terms, sort of more yucky to do. But that's the idea, and that's the real power of this new equation that we just developed. So now what I'd like to do is go back to an example that we dealt with before, which is the ring of charge. And so here I'm going to set up our axis like so, and make this the point X, and then draw our special ring of charge. If you remember, that's, you know, in the axis. So if this is X, it would be in the ZY axis. And so it's this sort of ring of charge set up in the axis. And so now what we want to do is we want to find the potential at point X from this ring of charge. And the way that this is set up is that it's set up so that basically, you know, any point on this axis here is going to be the same distance away from that point X. Okay, so it's the same geometry that we had in our ring last time. And so it's a ring of charge with radius A. And so this hypotenuse here for the ring of charge is going to be A squared plus X squared square root. Again, where this is the distance X, and then the A is just this distance here. So what's really nice is, so this is, you know, some ring of charge Q, is that you can think about the potential as just basically this whole Q is the same distance away from this point over here. And so if I want to express the potential, I can just sort of think about that each little tiny dq is basically going to be a contribution from a little piece of that ring, and just in a sense integrate all the way around that ring there. And so you can also sort of just think about it as being kq over that distance a squared plus x squared, like so. And that would be the electric potential. Again, because this q, right, every little piece of q is the same distance away. And what's nice about the potential is you don't have to worry about parts of it canceling. It just plumb adds up. And so you can think about that different ways. Maybe even a nicer way, if you wanted to, is you can think about is kind of doing what we did before, is doing a sum and an integral. So k dq over r. In this case here, that's my k constant, this is my dq, and I'm sort of like adding up little contributions from dq's, and this would be a squared plus x squared 1/2, and of course all of that's a constant, so just k a squared plus x squared, you know, to the 1/2 power, and it's just the integral over dq, which you can do in this case because the q doesn't depend on any of these factors, and so you just come out like this here. And so what's nice about this, and this is another very powerful thing about the potential, is that it's usually easier to find the potential. So this was actually easier than when we found the electric field from here, right? And the thing is, we have this equation now for electric field. So if I want to find the electric field in the x direction, it's the negative derivative of this with respect to x. And so I want to take the negative derivative with respect to x of this formula we just found, right here, and when I do that, so there's a negative sign out front, and I'm going to have my k and q, and so basically the derivative from this guy, I'm going to have a negative 1/2 power from the powers, and then a squared plus x squared, so this will end up being to the 3/2 power, and then I get a factor from in here of 2x. So, you know, make sure that you are sort of following along with how we did this integral. The negative signs cancel and the 2's cancel, and so I'm left with kqx over a squared plus x squared to the 3/2 power, which if you go back to our calculation on this is the same thing we got before, but this is an easier method. So in general, when you move on in physics, what you were sort of taught to do is try to calculate the potential and then take that if you want to find the electric field, and it's almost always easier to do it that way. Okay, and so just finally then, here is sort of a summary page of everything we've done for the electric potential, and then the equations relating electric potential and electric field. Just kind of a nice summary here. And what I'd like to do now is just go over, so at this point in class we would be doing this demonstration here. This is the Van de Graaff generator, and you can find lots of explanations about this. This is also one of those things where, okay, we're going to do it in terms of getting this ball, this big Van de Graaff generator, a huge positive charge, but you can do it the other way. It really makes no difference, and so it's just it sort of is the same. But what happens is there's this little belt in here that just mechanically goes back and forth, all right, and the belt over here, it comes across a little it's like literally like some pieces of like a little metal claw that rubs against it that's positively charged. And so electrons from the belt jump over to here, and they leave behind some excess positives. And then you come over to here, and there's another little metallic claw here. And what happens is these positives pull electrons from that metal ball. And you keep rotating this back and back, and basically it takes a whole bunch of electrons and makes this ball super positively charged. And then you can kind of do fun things with it. One of the things you can do is make sparks, and so I'll post a video of someone doing this, but I just wanted to kind of explain what's happening because it's kind of cool, and also it's going to be helpful to us moving on. And so basically air is an insulator, right? But the thing we didn't say about insulators is most insulators, if you give them a large enough electric field, will become conductors, at least for a brief period. And so the way we can think about this is with the air will ionize, and we call this the electrical breakdown. And so you can imagine that air are atoms with a positive and a negative, and in general it's not like a metal where you can get that negative out easily. But what happens is this Van de Graaff generator gets such a huge electric field, okay, which is the electric field needed to break down air. And what happens is the charges separate, they ionize, and then what you have is you have these electrons that are free. And so like in this case, what would happen is like this electron would jump to here, like this one would jump to here, and then you'd pull one from over here, and this sort of process happens with all the air particles. And what happens is you see a nice little spark across the, from your piece of metal. So generally what the person's doing is they have like a little piece of metal over here on a stick that's connected to the ground. Which literally means, you hear about this in terms of electricity and stuff. The ground is literally just put into the ground, and so it's sort of a huge source of electrons, or a place to put electrons. And so basically when you put this metal near there, right, this effect can happen, and what you're kind of doing is turning the air into a conductor for like a brief second. And so what happens is these charges will sort of go through here, making like a little circuit. You'll see the spark, and what that does is it, you can imagine it cancels out a lot of these positives. So basically, the electric field gets big enough to do this. You have electrical breakdown, and then those electrons come in here and sort of satisfy this guy for a while, and then it stops. And so this is the same sort of idea that happens, if you've ever had a static electricity at home where you actually saw a spark. It's the same sort of idea. So you basically on your hand got enough charge built up in order to sort of act kind of like a Van de Graaff generator and break down the air between you and like a doorknob or whatever it might have been. It's also the same effect that's happening with lightning. And just one last thing that's interesting is sort of a key part of this. So this is the number here. This is the electric field needed to break down the air. Okay, so it's pretty high, 3 times 10 to the 6th. And what happens is you'll actually see these sparks at electric field less than this. And what happens is, in general, there's particles coming down from space, which is kind of a crazy idea, right? But these particles can help this process. They sort of bump into these atoms and sort of make these atoms a little bit more unstable. And so you'll find that in practice, the breakdown will actually happen at values less than this. Okay, so I'll post a demonstration online of someone doing this. Again, you've probably seen this before, but if you haven't, it's some good stuff to sort of see. And again, this picture here is sort of our first electric circuit that we've seen so far. So we're going to move into that territory next.